This video is about GX diagrams or GX plots, Gibbs energy composition diagrams. Let's start by understanding what is Gibbs energy of a solution. Think about two elements A and B in their standard state, meaning at atmospheric pressure at whatever temperature that we are considering. What is the stable state of A and what is stable state of B? They are in that state. So here this is some crystal structure in which A is stable and B is also stable in the same crystal structure. What is the Gibbs energy of this mechanical mixture? Meaning A solid piece and B solid piece are together, and that is the system. It's not an atomic level solution or something, it's just two metallic pieces together. So this is called a mechanical mixture. Gibbs energy of this mechanical mixture is this, right? It's a rule of mixture addition, we say. Take mole fraction of A, multiply that with Gibbs energy, standard Gibbs energy of A. Similarly for B. So that is Gibbs energy of this entire mechanical mixture. What if these elements are mixed and form a solution like this, atomic level solution? What is Gibbs energy of this solution? It's going to be like this: XA GA bar plus XB GB bar. GA bar is nothing but Gibbs energy of A in the solution, right? It's partial molar Gibbs energy or chemical potential. We have seen that in the video on chemical potential and activity. So this is Gibbs energy of solution. This solution, let's call it phi. It's a binary solution of A and B, two elements. So Gibbs energy of the solution is G phi. This Ga bar, the partial molar Gibbs energy, can be written like this, right? Ga standard plus RT ln A in phi, means a function of activity, and for GB we can write this. So here we can see this Ga standard and GB standard. We can take them together, XA Ga standard plus XB GB standard plus the remaining terms. So what is this first part? This is nothing but Gibbs energy of mechanical mixture, right? This part. So when we talk about Gibbs energy of a solution, it takes in Gibbs energy of pure elements. This is the pure elements contribution plus something which comes due to mixing. So this is mechanical mixture Gibbs energy plus something else. This is due to mixing, right? We can call that delta G mix. Gibbs energy change due to mixing. Otherwise, Gibbs energy will be equal to only mechanical mixtures Gibbs energy. Okay, so this delta G mix, we have seen in the video on Gibbs energy that this delta G can be represented in terms of delta H and delta S. So here it is delta G mix in phi. So we can represent enthalpy change during mixing in phi and entropy change during mixing in phi at some temperature. In ideal mixing, what will happen? If the mixing that has taken place between A and B, if it is an ideal mixing, we know that delta H mix is 0. There is no interaction between A and B. We have seen that on video on enthalpy. So this delta H mix will be 0 for ideal mixing case. What about delta S mix? It is expressed like this. This equation comes from Boltzmann's equation for entropy, S equals K natural log of W, with some mathematical approximation called Stirling's approximation. For a binary system, it can come like this. R is gas constant here. Okay, this is per mole. This is represented per mole. We'll see little more about the expression for entropy change. So a delta S mix ideal is represented like this. What is this? It comes from K natural log of W, I said. What is the W here? It is different number of ways in which A and B elements can mix and still result in the same Gibbs energy. Okay, meaning the macro state is same, but how many number of ways in which we can arrange A and B randomly in a solution and arrive at the same Gibbs energy. That is the W here. So different atomic configurations. That gives rise to this entropy. So this is called as configurational entropy. This is the term used in different textbooks, but As we have seen in the video on meaning of entropy, this term configuration is quite generic, right? Can be used for tossing coins, how many different ways in which we get the outcomes. There is a configuration there, and different ways in which energy levels can be arranged. There is a configuration there. If you take an amorphous material which doesn't have any crystal structure, in that, even in space, the positions in space, they contribute to some configuration. There can be different ways in which atoms are arranged in spatial positions. So that is also called configurations. So this term is a bit generic for this specific case here, where two different chemical elements are mixing. For that, we can call it chemical configuration entropy. Okay, this term is not used in textbooks. If you want to learn more about this, I would suggest you to go to this reference. It is one of my recent papers where we talked about the need for bringing a term like this, chemical configuration entropy. Okay, fine. Now we'll see how this expression looks in graphical form. You can have delta S mix ideal in y-axis and composition in x-axis. It's going to look like this. So this expression, you can see, it doesn't have anything. It doesn't have temperature. So it is a function of only mole fraction of A and B. So here mole fraction of A and B are changing. So accordingly, the delta S mix also changes. It's a concave kind of shape with maximum in the middle. Okay, so this is delta S mix ideal. What is its contribution to Gibbs energy? When we talk about delta G mix ideal, it is delta H mix ideal minus T delta S mix ideal. The delta H mix anyway is 0 since it is ideal case. There is no interaction between the elements. So delta G mix is nothing but minus T delta S mix. If delta S mix is looking like this, you can imagine how minus T delta S will look. It's going to be a convex shaped thing, multiply the same curve multiplied by T also. We can understand Gibbs energy composition curves. Here we can start with A, and its Gibbs energy in standard state is Ga standard, and for B it is Gb standard, and in this x-axis composition is varying. What about this line? What does it represent? It's nothing but the Gibbs energy of mechanical mixture, right? Weighted average of pure element Gibbs energies. Xa Ga standard plus Xb Gb standard. What about this point? For example, here the composition is 50-50, 0.5A and 0.5B mole fraction. So 0.5 Ga standard plus 0.5 Gb standard will be the Gibbs energy at that point. Now imagine the solution like this. In the solution, if it is an ideal solution, what will be its Gibbs energy? It will be this curve, right? Which is nothing but the pure element contribution plus delta G mix ideal. This delta G mix ideal will have this shape. We know it comes from T delta S mix, and it has a negative sign also. So it is going to be a convex shaped curve like this. Okay, fine. What about real solutions? They will be deviated from ideal solution. For example, like this green curve. They can have quite complex shapes. For example, it can be convex in the beginning, again concave in the middle, again convex in the end, with the different levels of increase and decrease. So there are many ways in which Gibbs energy curves come. In intermetallic phases, for example, it will have a very sharp V at one single composition, not throughout the entire composition range. So there are different ways in which Gibbs energies come, Gibbs energy of real phases. How do we write the expression for this? Take the entire ideal mixing contribution, like pure element contribution, ideal mixing contribution. From this ideal mixing Gibbs energy, it is deviated to some extent, right? This deviation is captured in this term. That is delta G excess, delta G mix excess. So this excess takes care of all the interaction effects. We know that in ideal solution there is no interaction between elements. We talk about enthalpy of mixing being 0. Here in real solutions there will be some interaction between elements, and that is the reason why it deviates from ideal solution. Okay, and that is captured in this term delta G excess. All this is done at one single temperature. Okay, so this Gibbs energy composition diagram is for one single temperature, and this is a quite useful concept to understand many things in physical metallurgy. This is the thermodynamic basis for phase diagrams. We'll see it shortly. Now think about this Gibbs energy composition diagram. Take a point. So we are talking from pure A to pure B for the entire composition range. This is how Gibbs energy is going to vary. And at this particular point, if this is the overall composition, then what will be the Gibbs energy of it? It is represented by this particular dot. Okay, so which is this point. This is the Gibbs energy of that solution. So we can get it from Gibbs energies of individual elements. What does this tangent represent? It intersects with this axis and this axis. What are those points? Those are Gibbs energies of A and B in solution. Partial molar Gibbs energy we call it, right? And it can also be called as chemical potential of A and B. Now imagine another point and we can draw a tangent for that also. Okay, and talk about mu A and mu B, which are different now. So when the overall composition changes, mu and mu B change. What about the Gibbs energy? Gibbs energy at this point, that if this phase can be called as phi, Gibbs energy is G phi, and it can be expressed like this: XA GA bar plus XB GB bar, or XA mu A plus XB mu B, both are same, right? So what is this? This point, the value, the G phi, is nothing but this mu A value multiplied by this total extent is XB, right? This point is XB. So the remaining point, this entire thing, is XA. XA multiplied by mu A, this y-axis value, then XB multiplied by mu B. This is the XB value multiplied by mu B. So that is going to give this value here, this y-axis value here. So what does this line represent? The entire curve is above this line. So this is the minimum possible Gibbs energy. This, when A and B have this chemical potential and their combination is giving us this Gibbs energy, for this overall composition, this is the lowest possible Gibbs energy, and that is the equilibrium state. So the entire curve is above this line. That is the minimized Gibbs energy. Fine. Let's think about a slightly higher temperature, and we use orange color just to say that it is a higher temperature. The curve is going to look different. Imagine a point overall composition and draw a tangent mu A and mu B are the chemical potentials now. These are quite different from what we have seen in the previous overall composition. Now this phase phi is nothing but mixture of A and B, a solution of A and B, when pure A and pure B are also in the phi structure. Now I am using the word structure, not saying phi is a phase now, meaning this phi is the structure for AB also, the solution also. It can be a structure like FCC, like phase center cubic crystal structure. So that can be the stable state. We talk about standard state of A at this particular temperature, right? So at this temperature, A is FCC. If that is the case, then this GA standard is nothing but GA phi, phi being the FCC structure. Okay. So if that is the case, we can replace all these things with the phi on top. So the superscript phi represents, this is Gibbs energy of A, pure A, if A is in phi crystal structure, and this is solution of A and B in the crystal structure phi, and this is chemical potential of A when A is in crystal structure of phi. Okay. So entire thing is represented in terms of one phase label phi. Okay. Imagine another state alpha. A and B are now in alpha state, and the solution is also in alpha state. You can imagine something like a BCC structure for this. This is the Gibbs energy for this solution. So these points are Gibbs energy of A in alpha state, Gibbs energy of B in alpha state. The entire curve is the Gibbs energy of solution alpha with the different combinations of A and B. Imagine this particular overall composition. These are the chemical potentials of A and B, and the entire curve is above this particular tangent. Now we can think about competition between two phases, alpha and phi. Imagine you have A and B, you are trying to mix them in some ratio, and you want to see at this temperature what is going to be the stable state. Will it be single phase alpha, single phase phi, or will it be combination of alpha and phi? With respect to different compositions, what will happen? We'll see that. Imagine this overall composition. Here we have the composition in phi structure, the phi phase. Is it the stable phase? Draw this tangent to this green line and see whether is there anything below this line. Yes, there is something below this line, right? Which means this is not the stable state. There can be something lesser than this. Imagine this one, this point. Is this the stable state? This is in alpha, right? So is single phase alpha stable at this composition? Draw the tangent and see. Here we are seeing this green part is below the tangent. So that is also not stable. Now imagine this tangent. This tangent is common to both alpha and phi, and it is meeting at certain points in alpha and phi. And if our overall composition is this composition, if you put it here, you can see that this particular composition of alpha and this particular composition of phi, if these two phases are in equilibrium, two phases alpha and phi with certain composition for alpha and certain composition for phi, if these two are existing together, then we get the lowest possible value. You can see entire curve is above this tangent. All the parts of the curves, two curves, are above this tangent. Okay, meaning if the overall composition lies between this point and this point, in this white being anywhere between this and this, we are going to get alpha and phi in equilibrium. That is a two-phase equilibrium. Fine. What is mu A and mu B here? Is this mu of A, chemical potential of A in alpha, or chemical potential of A in phi? We know that when two phases are to be in equilibrium, chemical potential of A should be same in all the phases, right? So if mu A is labeled here, it means it is mu A of alpha and mu A of phi as well. Okay, so there is only one mu A we need to bother about. Similarly, one mu B. Okay, what about points beyond these two? Like we had these 2 points for two-phase equilibria. What about points to the right of it or to the left of it? Now let us consider this one, which is to the right of it. Now if this is the overall composition, draw a tangent. This is a tangent to only one curve, and the entire thing is above this tangent. That means this is the stable state. Okay, so single phase phi is stable for this overall composition. Similarly, okay, we can have a mu A, mu B here. Similarly, when we have this as our overall composition, draw a tangent. This is tangent to the single phase, and the curves are above this. So this is going to be the stable state, which is single phase alpha for this overall composition. So you can see with respect to different overall compositions, we are going to get either single phase alpha, single phase phi, or two phase alpha and phi in equilibrium. Okay, these are the chemical potentials. Fine. Now we will see how this Gibbs energy composition diagram can be the basis for phase diagram. So in the left hand side we have Gibbs energy composition diagram with the overall composition of this point. When two phases are in competition, the curves are intersecting. And in the right hand side we have temperature versus composition diagram. So this is the phase diagram. We will see how this forms the basis for this phase diagram. So look at these 2 points. These are compositions of two phases which are in equilibrium when your overall composition is in between these two compositions. Okay, so take those compositions, and this is the temperature at which the entire diagram is drawn. Here we have temperature as the axis. So this entire diagram is going to give information for this diagram for one temperature. So that is this temperature. Let us take it. Let's say this is that point. This temperature is the point at which the Gibbs energy composition diagrams are drawn. So this information of these 2 points can be taken and mapped here. The same compositions, XB values are here. And what does it represent? This point represents this alpha's composition when it is in equilibrium with phi. This point represents the composition of phi when it is in equilibrium with alpha. So this is alpha, this is phi. Let us label that also. Okay. So this information about two-phase equilibria we got from Gibbs energy composition diagram. Like that we can get even single phase equilibria information. We will see one more example. Here we have a Gibbs energy composition diagram here at some temperature T1. There are two phases in competition, solid and liquid, again in a AB system. This is the phase diagram, temperature versus composition in a AB system. Okay, we will map information from this to this diagram. Here we have temperature T1, and throughout the composition range, this liquid phase is below. So if you look at Gibbs energy minimization, we don't need to bother about solid at all here. Throughout the entire composition, liquid is the stable state. That's the meaning of it. Okay. Even if you draw at each point a tangent and see, you will get in all the points liquid is the stable state, and the entire two curves will be above that tangent for any point. Okay. So liquid is the stable state throughout the composition range at T1. This is the information. Let us map it in the diagram. So this is the temperature T1, and liquid is the stable state throughout. So let us put an orange line here. In fact, we don't actually draw lines like this. Only for two-phase equilibria or multi-phase equilibria we get the points. For single-phase equilibria we don't generally draw a line like this. This is just to understand. Here the orange line throughout, which is liquid. Now think about this one. This is at a temperature T2 where the two curves intersect, solid and liquid. So there is a range over which solid is stable, and there is a range over which solid and liquid are in equilibrium. There is a range over which liquid is in equilibrium. So this information can be mapped now against T2. Okay, so this is the temperature T2. Against that, there is a range over which solid is stable. There is a range over which solid and liquid are in equilibrium. There is a range over which liquid is stable. Okay. So in between these 2 points, there is a two-phase equilibria. There is a different color for that. Now look at this temperature T3, where solid is stable throughout. So this is the temperature T3, where solid is stable throughout. Okay. So like this, we can do at different temperatures and get the information of phase equilibria and map it to the phase diagram. Like this. So if we do it at different temperature, these are all single temperature data from this temperature, some other temperature. So we can get the lines at which liquid phase compositions which are in equilibrium with solid, and these are the solid phase compositions at different temperatures. Okay, from this temperature to this temperature. So like this we can get information and draw lines like this. So this line connects all the points of the composition of liquid which is in equilibrium with solid. Similarly, this is the solid phase composition, and we know that above this line whatever we have is single phase liquid, and below this line entire thing is single phase solid. So we can label it like that. So this is liquid, this is solid. In between S plus L, solid and liquid coexist. This is how we get a phase diagram from Gibbs energy composition diagram.